Hey, this is Chris Cal. It's currently Wednesday, June 20th, 2018. It's only halfway through my second week, but there's been so many things that I've learned in the last 3 days and over the weekend that I figured I'd make a video right now. So let me just show you some of the stuff I've been working on. My task on the team right now is primarily focusing on the simulator. So here is the MIT tunnel track. So this is the tunnel track. Let me restart it so I can just show you what it looks like. So basically, I have ROS-core running normally. Over here, I'm going to stop this process. And then let me also close this window. That was for my ROS bag. ROS bag is used to record stuff, record all the nodes. But essentially, let me first do a, let's see, ROS launch, where is it? While following the launch. So this will close, give me a sec. I gotta CD into desktop and then go into Sims workspace. It's good so that way you can see what's going on. So if you ls, you'll see that this is my ROS directory. I think I sourced, but if I didn't source it, then it won't work, but we'll see. All right, that's fine. Let me just source this file. Let me first do a cat can make. So cat can make will basically build what I currently have. And by what I have, I'll probably need to show you so you know what I'm talking about. What I have right now is I've basically created this Sims workspace, and inside of here we have build, develop, install, source. Source is where all my code is, and all of these are GitHub repositories except for custom. Writing custom while following, because the idea is that when we're developing this F1 temp course for Penn, if I end up taking this class, or I'm definitely helping out build out the class, we'll definitely need to have a pretty robust understanding of how the assignments are created, even though we already have code for this. So I borrowed a lot of code. It's not all mine, but essentially we have these three files. We have control.py, PID and simconnector.py. Now in terms of how these connect, I can actually show you visually right now. So let me pull up some of the files. So if you look at this was actually made with the RQT graph. And if you look at it, you'll see that normally the Gazebo, which is a simulator, will publish onto a topic called scan because we're not using an actual lidar camera in the simulator. Scan is normally by lidar. Now in the real world, this would not be coming from Gazebo, but actually from the Hokuyo URG. But in this case, we have a scan. The scan goes to what was called a Levine demo node. The name didn't make sense to me, so I renamed it to PID error, because basically it's using the proportion integral derivative algorithm in order to determine how straight a car should be. And just a visual of that is, if you imagine there's a car, you want to have it follow a wall. Basically, PID will try and determine, first of all, what's your desired trajectory? So let's say desired trajectory is like a foot away from the wall. But to stay a foot away from the wall, we're going to use laser scanner, shoot out 2 rays, and essentially it will determine what's your angle of your car, and more importantly, what is the parallel distance to the wall. If the parallel distance is not equal to desired trajectory, if it's too much or too little, the car will adjust itself by steering, which is super cool. And so basically that's what this does here. It calculates the error. That's why the topic is called error. And then it goes into the control node, which the code looks generally like this. The control node will basically take things like the angle, and here it's limiting the angle to 30 degrees. Here it's changing the velocity. So if you're making a tight turn, slow it down to 2, I believe this is units in feet per second, but MIT docs say meters, not sure. Otherwise, if you're going like pretty damn straight, about less than 1 degree, then velocity up to 10. So that's what control generally does. In SimConnector, I haven't changed at all because it's really just taking the data and just changing it to a different data structure so that it can go directly into the Gazebo. So now that I've built, let me make sure I source. You always need to source. Normally I should have sourced already, I'm pretty sure, but just for the purpose of this, I can also show you. This is what it looks like. So source. I'm going up to my ROS launch while following.launch. So this works now. Here it is running. This Gazebo in the background should probably close soon. In fact, if it doesn't, let me even like manually close it. Actually, let me, all right, so Gazebo just opened. I had to manually close it so it would restart. And there it is in the world. Now the thing is that I think I messed up because I didn't initialize correctly, so let me redo that again. And that way you can get to see it again. So I'm gonna do Control C, it's closing this script, it's a launch file. What is a launch file, by the way? While I'm waiting for this to close, let me show you what a launch file looks like. So launch file is basically like a script in order to run things, because if you didn't have a launch file, every single node would have to be initialized manually. And when we have about 10 to 15 nodes, you don't want to be opening up 10 to 15 terminal windows. So let's see, let me force quit this Gazebo. So what I wrote was while following that launch, and it looks like this. So you notice how in here, we first launched the World Race Car Tunnel. This is taken from MIT's 2016 race car. This, I actually found out this was a mistake. I fixed it. This allows us to use tele-op joystick commands. And before it was missing the low level and the VESC in front. After doing that, it was able to connect it so you didn't get an orphan node, which was a term that Matt used, pretty cool term. And then down here are those three files I showed you earlier, PID error, control, and sim connector. In no particular order, although in this case, it does follow the ordering from left to right here. I'm not sure if it actually makes a difference. One thing I did realize is that there's this thing called output equals screen, which wasn't there before. Only one of these three by default had it, so I was only seeing print statements from one of the nodes from control.py and was getting very confused. Now it turns out that we have to put output equals screen to all three of the nodes so that print statements show up. Spent all day yesterday, not all day, but spent a significant amount of time figuring it out, and now I finally figured it out, so it felt really good this morning seeing that. So let me run this again. So I'm gonna ROS launch that while following, and now when we launch it, hopefully it has a new version of the code, by the way. Let me make sure it's set to like, because I temporarily made it stop moving so that I could log all the info. It should be good now. Keep this in the background too. So notice how here, first of all, we're seeing all this data. I don't know why the car is starting from weird spots. You need to actually figure that out. But essentially you can see the car moving, it's following this left wall. It normally goes counterclockwise, so there's definitely something wrong. In fact, if I had to guess, I would say what's wrong is that we just have something else running that we shouldn't have running. AKA this thing over here. That was the problem. Let me see what other terminal windows are open. We have a ROS core running, this not running anything. So if I do this again, it should work now. Alright, so apologize for that, but I definitely need a hang of this. So here it goes running again. Preparing the world, super cool. We're here, it's running this code. This is just updating constantly. Basically, it's reading in lidar scans and then outputting information and doing a callback function. So here we have the robot. I think each of these grids is about 1 foot by 1 foot because the rope, I'm not sure actually, because we define robot length as 1.5 feet, so that might not be right. But here we have the robot turning. So it's following this left wall and wants to stay 1.5 feet away. Seems to be doing that pretty well. And you notice over here, there's this caveat where this thing could cause a problem. Somehow by using 1.5 feet, it solved the problem, and by also doing a future distance. You notice on this paper, that projection of the car forward, we're basically having it look forward and predict, and sometimes there can be a slight delay. So we see this robot turning, and it takes about like 2 to 3 minutes to run through the whole track, and I've already sped up some things by allowing velocity to get fast when it's going straight. Notice how now it's suddenly going a bit faster. So something to note, one of the biggest challenges on this tunnels course is this right turn here. We normally wouldn't expect the robot to be able to come down straight away and then make a right because it's following the left wall. I would have normally intuitively expected the robot to come down, keep following the left wall, and just ram right into this wall. But what ends up happening is it somehow detects that this wall ends and goes this way, and because it's shooting out lasers at a particular angle at 60 degrees from center, it will basically follow this right turn, which I was very happy with last night. And so let me just demonstrate that to you. So here's the robot. Let me zoom in a bit. You can notice that when he gets here, hopefully it'll make it. All right, that one didn't make it that time. I think I was going too fast right there. You saw the speed going too fast. But essentially normally makes it, and then it'll do a left turn. Probably didn't make it because they changed the velocities. There's definitely a lot of testing to do. But what's more important than this, let me just quit this in the meantime, is that we want to be able to test this in the real world. So Jack's gonna be, after Friday when I get the simple simulator up and running, simple wall following, Jack's gonna then take the robot into the real world. He has a version of the car as well. I have one that I built with a lot of parts I bought, like the chassis and stuff, but using Lab's car, we're gonna take, not this one, but the second floor of Levine. So the M Lab is right here, and we've seen videos on the F110 site where it goes around this corridor. Normally in the video it's going in a clockwise fashion, but we can also make it counterclockwise because that's more of what a race is like. Do a left wall follow. We will have to be careful of people, and we will also need a 3D model of the world. I asked Manas, but I'm not sure if we have a 3D model of this. Technically, I mean, it's actually not that easy because we want to be able to model all these random corridors and doors so that we know that the robot won't crash into those in the simulator. So that will be determined. Asking Manas, so we'll figure that out. A couple other things I'll show you though is in terms of the car, generally it looks the same right now. I did find out that this anchor thing, I think because it's metal, when I plugged in the remote joystick, the Logitech F710, was having huge frequency problems. Over 2.4 gigahertz, I was only getting about a foot of range. But when I used a plastic USB hub, it was getting like across the room. I also picked up the Z camera on eBay for about $290, and normally it's like $450. So this is what I'll be using when I eventually get to the convolutional neural networks. But right now, haven't gotten to that stage yet. Right now, I'm just doing control, helping develop the course. So this will be something for later. So that's super cool. Here's all the hardware from McMaster car. I haven't had much use for it right now because I basically finished assembling the car. So that's basically that. Let me see if I have any other documents. I mean, I've printed out this whole stack of papers now. I'm reading through some of the things. Basically, I'll be at the lab from like 9 to 5. In the morning, I wake up around 7 like today, and I spend about 2 hours getting a head start. And then at nighttime, I'll do a lot of readings and watch videos. So currently on my computer, you'll see that, I'm gonna watch this preseason webinar. I still need to go through these lectures here. It'll be super cool. And down here, we have all the simulator setups. I printed out all the MIT 2016 guides, so I'll be reading through those. Last night, or 2 nights ago, I was reading the paper on the Dave autonomous robot from 2004. So I've been reading this on how they used the convolutional neural net back in 2004. They actually used a Traxxas chassis, which is really cool. And they basically trained it to just drive in the backyard. This is what I wanted to do originally. The course is going to be more about controls so that we can, better understand the PID framework and eventually optimal racing lines by using waypoints. That's what I'll be working on next week after the simple wall following works. But it's actually, this would be cool, but after a while, even if it were successful, it'd be kind of boring just watching it going and like driving in the backyard. It'd be kind of cool giving the robot direction. So I'm actually pretty happy with what Professor Mongram is giving me in terms of getting it to try and navigate some type of map. So in this case, it's already pre-mapped out, but in races, it might not be. But teams are allowed to use waypoints. I don't know exactly what I'm saying right now, to be honest, because a lot of this I'll be picking up next week, but just wanted to give a little preview. So in conclusion, and also one more tip is every day I've been pushing to GitHub because in case this computer dies or runs out of battery all of a sudden, or I accidentally flash it again, I don't want to lose all my files. So it's all pushed to GitHub right now. And the Slack has also been great in terms of asking people for advice. So thank you.